Welcome to this course titled Mathematics for Chemistry. I am your instructor, Dr. Madhav Ranganathan, and I am from IIT Kanpur. I will be going through this course consisting of 40 lectures. First, I will give a brief outline of the course, and then I will start going through the entire course. The title of this course is Mathematics for Chemistry, and it's a typical course taught in the chemistry department. The format of this course will be video. I'll be using primarily the blackboard behind me, or you can call it a green board, and all the lectures will be in video format. I am your instructor for this course, and my name is Dr. Madhav Ranganathan. I am from IIT Kanpur, and this is my mail and telephone number in case you need to talk to me. The course will cover all the standard mathematical techniques that are typically used by chemists, and in addition to doing the basic mathematical techniques, we will also cover a lot of applications. The topics that will be covered, they include linear algebra, differential equations or partial differential equations, integral transforms, group theory, and data analysis. Now, it is very important that a student coming to this course has some basic prerequisites, and I will be assuming that you are familiar with all the mathematics that is part of the standard BSc chemistry curriculum. And in particular, I will be assuming that you know some basic linear algebra, you will know about scalars, vectors, and matrices, and some basic operations involving these objects. You will know techniques of integration and differentiation, and you will have some familiarity with complex numbers. Okay. So, this course is essentially an MSc level course. So, it's taught in MSc in most universities and IITs. So, I'll be expecting that all the standard BSc mathematics is familiar with you. There are some textbooks or reference books which I'll be following, and I won't be following a single textbook throughout the course. I'll be using various books. I'll be taking from some internet sources also, and some other notes that I have prepared on my own. So, but there are some very good books in this topic, and you are well advised to read one or more of them. There is a book called Mathematical Methods for Physicists by Afkin and Weber, and it's a really exhaustive book with very nice applications in all areas, particularly pertaining to physics, but they overlap with some of the applications that we described. Then there is a book called Advanced Engineering Mathematics by E.L. Kreyszig. This is also a very good book, and it's one of the books that is used in the first year engineering studies. Okay. Then there is a book called Mathematical Methods for Scientists and Engineers. This is by D.A. Macquarie, and Macquarie has written lot of books in physical chemistry, and so a lot of the applications that he talks about are related to applications in chemistry. So, these are general books on mathematics, on the mathematical areas, especially linear algebra, differential equations, and integral transforms. Then there is a book that is particular to group theory. It is called Chemical Applications of Group Theory by F.A. Cotton. It's really the Bible for group theory in chemistry. So, we will be spending nearly about 15 lectures on group theory. So this book is an excellent book to have, whether you are a physical chemist, organic chemist, or inorganic chemist. This is one of the standard books on group theory. In addition to these books, there are a lot of sources on the internet, and I am pointing out two hyperlinks. These are, the first one is mathworks.com MATLAB. So, MATLAB is a common mathematical, it's a common programming language which also has lot of inbuilt mathematical operations. And the reason I put this is that lot of the lot of the things that you learn in this course, you can actually implement some of them using MATLAB, and that will strengthen your understanding. Similarly, there is another program called Mathematica, and so this mathworld.wolfram.com is the site of that program, Mathematica, and both these websites have a lot of information on the actual theory behind the mathematics. So both these websites are very good to learn mathematics, in addition to actually doing small calculations. One of the nice things in Mathematica is you can do what is called symbolic mathematics. You can actually give a function and ask it to calculate derivatives or integrals. Okay, and so this proves to be very useful when you want to learn new mathematical methods. There are additional readings. There is Mathematics for Chemistry by C.L. Perrin. There is a book on symmetry and group theory by Carter. Then there is Mathematics in Chemistry by K.V. Raman and S.B. Pal. There is Group Theory and its Applications to Chemistry by K.V. Raman. And again, I want to emphasize that these techniques have been around for many years. So you might find new books coming up all the time. You might find internet resources that are very helpful, and sometimes you find you learn these things from very unexpected sources. Okay. The detailed module wise plan is given below. So these are the details of the contents that I will be covering. So each lecture that I give will be approximately 50 minutes and 50 minutes to 1 hour, and it will be in video format. So at the beginning of each lecture, I try to summarize some of the things that we have learned in the previous lecture, and I have divided this course into various modules. Actually, the whole course goes in one flow, but you can learn specific topics by going through specific modules. Okay. So each module is in some sense self-contained set of lectures. Okay. Now the first, second and third modules, they deal with linear algebra. Okay. The first module it consists of 4 lectures. We'll be talking about scalars and vectors, and these are basics of vectors, and I'll introduce the abstract idea of a vector space. Then we'll talk about vector products, we'll talk about linear independence basis, we'll introduce functions of vectors, and then we'll talk about curvilinear coordinates. I am introducing curvilinear coordinates in this topic because it is something that is used very widely in chemistry, and this is a good place when we introduce functions of vectors. It's a nice place to introduce curvilinear coordinates. One application I'll be doing is the use of center of mass and relative coordinates, and I'll be talking about spherical polar coordinates. In module 2, which is 3 lectures, I'll talk about advanced operations on vectors. We will be talking mostly about vector integration and differentiation. I'll talk about 3 ways of taking derivatives of vectors: gradient, divergence and curl. We'll talk about line integrals, surface integrals and volume integrals, Green's theorem, Stokes theorem. And the applications that I'll be dealing with are related to force, work and potentials. So there's a theory called potential theory, which says how force can be calculated from the gradient of the potential. I'll also talk about the Laplacian in spherical polar coordinates. So the Laplacian is related to the second derivative, and what the expression for that in spherical polar coordinates. And again, this is something that is seen a lot in advanced quantum chemistry courses. In module 3, there will be 5 lectures. I'll be talking about matrix algebra. I'll be talking about matrices, system of linear equations, rank, Gauss elimination, determinants, inverses of matrices, eigenvalues, eigenvectors. I'll be talking about some special matrices like orthogonal, unitary, symmetric and Hermitian matrices. So all the topics related to matrix algebra will be covered in these 5 lectures. I'll be looking at applications. We'll be looking at Slater determinants, Huckel, molecular orbital theory. So the first 3 modules cover all the topics of linear algebra, and this whole set of 12 lectures is a complete set of lectures for somebody who wishes to learn all the techniques of linear algebra. Then we move to the next topic, which is differential equations, and so modules 4 and 5 will mainly be talking about differential equations. In module 4, I will have 3 lectures. I will talk about first order differential equations. First order ODE stands for ordinary differential equations. I will be talking about separation of variables, integration factors, exact differentials, a system of ODEs solved using matrix methods, and one application I will do is in reaction rate theory. In module 5, there will be 5 lectures, and this is the topic of second order differential equations, and second order differential equations are extremely common in chemistry, particularly quantum mechanics, and you need good techniques in order to solve them. So, we will be talking about second order differential equation with constant coefficients, the general solution, particular solution. Then we will talk about the power series method. We will talk about an application of the power series method is in the Legendre differential equations, and then we will talk about Legendre polynomials, and then we will discuss about singular points and the Frobenius method, which is an advanced power series method. So, this covers the set of techniques that are used to solve second order differential equations, and again this is very widely used, especially in quantum mechanics. So, we will be talking about angular momentum eigenfunctions of a single particle as an application of second order differential equation solution. Then module 6 is about integral transforms, and this is a set of 4 lectures, and I'll first introduce the idea of orthogonal functions, and this is the Sturm-Liouville problem, and then I will be talking about basis functions. We will talk about Fourier and Laplace transforms, and we will introduce Dirac delta functions. So, this set of topics is slightly more advanced, but an understanding of this topic will really make things a lot easier in quantum mechanics. So, this topic in a sense connects differential equations and linear algebra in a very natural way, and so very nice way of looking at the postulates of quantum mechanics, and you can look at position and momentum representations of the wave function. We will look at the role of Fourier transform in spectroscopy. So, in these 12 lectures I will be covering all the topics related to differential equations, okay. And then the next 15 lectures or so we will be talking about group theory, which is a completely different topic from these from linear algebra and differential equations, and in fact you will need a different book in order to study group theory. So, modules 7, 8, 9 and 10 will be basically talking about group theory and its applications in chemistry. Module 7 will consist of 4 lectures that will introduce the basics of group theory. We will talk about what is a group, what is a subgroup, what is multiplication table, what is meant by symmetry operations, what are classes. Then we will mention molecular symmetry and group representations. And an application, we will see the boron trihydride molecule. I want to emphasize that in all of group theory we will be constantly looking at molecules and seeing their symmetries. So, it is really not we will be doing applications along the way. So, and so they won't be separately mentioned. So, in module 7 we will talk about the basics of groups more from a mathematical point of view. In module 8 we will get into symmetry groups of molecules. We will talk about equivalent atoms, equivalent operations, the Schoenfly symbols which is used to denote the symmetry group of molecules, and we will mention how we identify the symmetry groups of molecules. So, suppose you are given a molecule with a certain geometry, how do you identify which symmetry group it belongs to? In module 9, which is 3 lectures, we will be going into detail about the of how we generate the group character table. So, the character table of various groups is found in most standard physical chemistry books, and what we want to do in module 9 is to understand how you work out a character table. So, what is the meaning of each of those things and how you work each one of them out. So, in order to do that, we will start with representations. We will talk about irreducible representations, the great orthogonality theorem and its consequences, and then we will show how we can use that to generate the character tables. So, so these 3 modules 7, 8 and 9, they together cover the basics of group theory and how group theory can be used to generate what is called the character table. So, in a sense the goal of these 10 lectures is to help you generate the character table. Okay. Now, the next 5 lectures is actually trying to use the character table for various applications. So, these set of 5 lectures we are talking about group theory and quantum mechanics, and in this we will talk about the postulates of quantum mechanics. We will talk about operators, linearly independent wave functions, symmetry operators. So, all the symmetry operations that are characteristic of the character table will be seen as operators. We will talk about direct product, spectroscopic selection rules, symmetry adapted linear combinations, projection operators, basis for irreducible representations, and then as an application we will look at pi bonding. Okay. So, so in these 15 lectures from module 7, 8, 9 and 10, I will be covering the entire I will be covering a significant part of group theory and its applications in chemistry, definitely at least at a substantial level, so that you will be able to use it in applications. Finally, in module 11 is just one lecture which is for completeness. I am giving this one lecture. This is on data analysis, and this is actually it is extremely important for all scientists, whether be it a theorist or an experimentalist. And what I will talk about is when you make various measurements, you get various data, and what do you do with that data? How do you do proper statistics on that? Okay, so we will be talking about average, mean, standard deviation, error estimates, and I will touch upon significant figures because it is a topic that is not very well understood. Okay, so I will just spend one lecture on this, and that will complete the set of 40 lectures that constitute this course. Okay. And well, once again I want to say that these are divided into modules. So, if you have specific topics that you want to learn, you can just follow the lectures of those modules. There will be some overlap, in the sense I will be referring to content from one modules when I am discussing another module, but for most part each of the modules are fairly self-contained. Okay, so let us get started with this course, and before I start the topics, I want to make a few general comments on why we have a course called Mathematics for Chemistry. Traditionally, mathematics has been a part of chemistry, and in particular in physical chemistry, but the kind of mathematics that has been used in traditional chemistry has been very intuitive and fairly basic mathematics. So, for example, you need some basic theory of differential equations when you formulate kinetic rate laws, or you are doing thermodynamics, and so on. And lot of the applications of mathematics in chemistry are things that you just learn as part of your regular mathematics, as part of your regular chemistry curriculum. And traditionally mathematics has been very intuitive, and you never needed a course called Mathematics for Chemistry. But things changed significantly after in the early 20th century, and when there were two new disciplines that were added to traditional chemistry. The first was quantum mechanics, and the second was statistical mechanics, and these two disciplines became an integral part of chemistry. And these two disciplines in particular are characterized by a mathematical basis at the very foundation of the discipline. So, for example, if you want to learn quantum mechanics, you need to know linear algebra, you need to know differential equations, you need to know fairly advanced techniques of solving differential equations. You need to know how to do matrix operations and so on. It's not something that you learn during your regular high school or undergraduate curriculum. This is something that you have to learn in particular. You have to learn techniques of how you solve complicated differential equations, and some of these techniques are fairly involved, as you will see during this course. Okay. So for this reason, it has now been realized that chemists need to know mathematical techniques. Okay. And for this reason, we have a course called Mathematics for Chemistry, and this is now a standard part of almost all universities. Okay. So with this basic comment, I want to move to the first topic for this course, and that is vectors. Okay. So we'll be talking about vectors, and now you all probably many of you have heard about vectors. You learned that scalars are objects that have only a magnitude, and vectors are objects that have both a magnitude and a direction. So the way you think of it as scalar as some number. So scalar has only magnitude, whereas vector is an object that has a magnitude and a direction. So a scalar can be a number like 3.5, 7, minus 5, etc. So it is some number, whereas a vector has both a magnitude and a direction, and it's typically represented by arrows. So you show arrows for a vector. Okay. And typically, if you're dealing in 3-dimensional space, then you say a vector has 3 components. So you write a vector v in the form of its 3 components. You can call it the x component of v times I, plus the y component of v times j, plus the z component of v times k. So you write vectors in terms of its components, and what you have are these unit vectors along each of the coordinate axis, which tells you the direction of the overall vector. Okay. So then what you do typically is you show a coordinate system where you will have the x axis, y axis, and z axis, and this vector v will have various components. This will be vz, this will be vy, and you will have a component along vx. This is vx. Okay. So you show the various components of the vector in this form, and we say that the direction of the vector can be calculated if you know each of the components. Okay. So there are 2 ways you can represent the vector. You can represent it as vxi plus vyj plus vzk, or you can write alternatively, you can write the same as vx comma vy comma vz. And it's to be noted that Vx, Vy, and Vz are all scalars. Okay. So vx, vy, vz are all scalars. Okay. But when you take a combination of them, you get a vector. Okay. An ordered set of them, you get a vector. Okay. So this is what you are probably familiar with how we understand vectors. And what we will see in this now is that we want to generalize this concept. Okay. And there are many ways to generalize it, and we can ask the question, this is a vector in 3-dimensional space, can you have a vector in 2-dimensional space? And the answer is yes, you can have a vector in 2-dimensional space. So you can have a 2D space, and there you will have you will have only two components. So, for example, if you have W, a vector in 2D space, it will have only two components. So, you can have Wxi plus Wij, okay, or alternatively you can write it as Wx comma Wy. Okay. So, vectors can be either in 3-dimensional space or 2-dimensional space, and the obvious question that arises is, does it have to be 2 or 3D? Can it be 4D, 5D, 6D? And the answer is yes. There is nothing that says you should have only 3 dimensions. You can have 4, 5, 6. You can have vectors in arbitrary dimensions. Okay. And so we are led to this idea that vectors can be 2D, 3D, 4D, and so on. A vector in a 1-dimensional space is nothing but a scalar. If there is only one dimension, then you have only one component and it is just a scalar. Okay. So, vectors can exist in all these dimensions. Now, this way of thinking of vectors turns out to be useful, but it is a little restrictive, and what we want to do is to give the formal definition of a vector as an abstract object. And once we do that, then we will see that it immediately gives many more objects that are also vectors. Okay. So in order to motivate this, you ask a question, you ask yourself this question: can I take a vector in 3D space and add another vector to it? Okay. So, if I take a vector in 3D space and add another vector in 3D space, I will get another vector in 3D space, right. So if you add these two vectors, you get another vector. Now, the question is, if I take a vector in 3D space and add a vector in 2D space, can I do that? And the answer is obviously no, you cannot do that, okay, because they are in different spaces and you cannot add them. So this motivates us to write the axioms of vector space. Okay. So we want to give a formal definition of a vector, formal definition of a vector. Okay. For initially, I'll be focusing on vector with real components. So, what is meant is that the components of these vectors Vx, Vy, Vz, etc. are all real numbers. Okay. So the formal definition of a vector with real components, and the advantage of doing this is that it's a definition that will hold for vectors in all spaces. It's a definition that will hold for all types of vectors also. Okay. So the formal definition is a vector is an object that belongs to a vector space. So a vector is an object that belongs to a vector space, and clearly this formal definition immediately leads us to another question, that is, what is a vector space? So what is a vector space? Okay, so what is a vector space? A vector space is a space. For example, the 3D space, what we talk about when we mention 3D space, we implicitly mention this 3D space is actually a vector space. So each object, each vector belongs to this 3D vector space. Okay. So now we want to come up with a formal definition of this vector space, and in order to do this, we want to give a very general definition that will hold for all kinds of vectors. Okay. And it won't be restricted to 2 or 3 dimensions, so you can use it for any dimensions, and what we will see is we will try to find out, we will try to give some basic properties of vectors, and if if vectors satisfy those objects, if any object satisfies those basic properties, then it is a vector that belongs to a vector space. Okay. I'll be restricting to what are called as real vector spaces. Okay. And in the real vector space, each of these components I said are real, okay, but you can easily extend it to vector spaces consisting of complex numbers. Okay. So, let us talk about the definition of a real vector space. Okay. So, now I am going to introduce the axioms of a real vector space, and this is going to sound a little abstract, and it is abstract. So, we are going to generalize it. So, we are going to give a very formal definition, and this definition might initially seem a little puzzling, but over time as you use it, you will become familiar with it. You will realize the advantage of having such a general definition. Okay. So, a real vector space So, a real vector space is a collection of objects. Okay. It is a collection of objects and later on we will see that these objects are nothing but vectors. So, it is a collection of vectors, okay, that satisfy the following axioms. Okay. So, the axioms that they satisfy are: first, if A and B belong to the real vector space V, sorry, it should be V. Then I will say CA plus DB also belongs to V, okay, where C and D are scalars or real numbers. Okay. So, let me go through this again. If A and B, okay, and I have denoted them by arrows. So, A and B are objects that belong to the vector space, and later on we will call these objects vectors. So, if A and B belong to this real vector space V, then any linear combination of A and B also belongs to V. So, you take any two scalars C and D and you multiply A by C and D by B, okay, then this object also belongs to V. Okay. We'll use a short notation for this. We'll say that if A comma B belong to V, okay, then CA plus DB also belongs to V. Okay. So, this is the short notation for this long statement, and we will be using short notations from now on. Okay. So, this is one axiom, and you can easily verify this for the 3D space that you are familiar with. So, if you take any two vectors, you multiply one vector by a number, multiply another vector by another number, okay, and you add them up, you will always get another vector. Okay. So, this is the first axiom. The second axiom there exists an object which we will denote as a 0 vector in V such that A plus 0 equal to A for all A. Also for all A belonging to V, there exists minus A belong to V such that A plus minus A equal to 0. Okay. So, the second axiom says that there is an object which we call the 0 vector. Okay. So, 0 is a vector which is also belonging to the vector space, okay, such that you add the 0 vector to any other vector, you will get the same vector, and for all the vectors belonging to V, there exists another vector called minus A vector, which you add to A vector, you will get 0. Okay. So, in other words, you can take any vector, you can always find a vector such that when you add those two vectors, you will get the 0 vector. Okay. So, this is the second axiom. The third axiom, actually this is a set of axioms, and in different books, sometimes books break up these axioms into various axioms, but I'll just show these as 3 axioms. The third axiom is a set of axioms that have to do with properties of this addition and multiplication. Okay. So, these have to do with commutativity, associativity, and distributivity. So, I'll just write them down, and they are fairly obvious. So, suppose you take A plus B, that is equal to B plus A. Okay. So, in other words, addition of two vectors is commutative. Then if you take A plus B and you add C to it, this is the same as taking A and adding B plus C. Then you take a scalar and multiply it to A plus B. This is the same as CA plus CB. Then you can take C1 plus C2, add it to A, you will get C1A plus C2A. Finally, you can take C1 into C2A, this is same as C1 C2 into A. Okay. Finally, you take a number 1 multiplied by A, you get back A. So, 1 is a scalar 1. Okay. So, these are the other axioms of a vector space, and these are also fairly obvious, and they are satisfied by most vector spaces. So, these are the axioms of a real vector space. Notice that the space is actually the collection of all vectors. So, if you add two vectors, you will get a third vector, and if you multiply by different scalars, okay, you can get all possible vectors. Okay. So, it is the space really refers to the set of all possible vectors. Okay. So, that is what is the vector space, and that's how we understand the 3D vector space. We think of all possible vectors, and the combination of all of them forms the vector space. Okay. These axioms can be understood in a very intuitive manner. Okay. So, it looks a little abstract, but really all that we are saying is that the first axiom is saying that you take two vectors, you add them, you will get a third vector. You multiply a vector by a scalar, you will get another vector. Okay. So, basically this axiom is saying that the vector space is closed to addition and scalar multiplication. Okay. And this in some sense this is the most important axiom of the vector space, okay, that you add two vectors, you get another vector, you multiply it by a scalar, you get another vector, and this is nothing but a combination of those two conditions. Okay. Then axiom 2 talks about the 0 vector, which should also be part of the vector space, and the inverse or the negative vector. So, corresponding to every vector there is a negative of that vector such that you add them and you get 0. Okay. The third axiom or the set of axioms refers to the properties of the addition. So, addition should be commutative, it should be distributive, and then the scalar multiplication should be distributive. Okay. And similarly, when you add two scalars and multiply it to a vector, it is same as multiplying by each of the scalars and adding the two vectors. Okay. And similarly, scalar multiplication is also distributive, and there is a scalar called 1. 1 is a scalar, it is not a vector. 1 is a scalar that you multiply by any vector, you get the same vector. So, these are in some sense very intuitive and very obvious. So, really the crucial part of definition of the vector space is that it should be close to addition and scalar multiplication. Okay. Now, what we will do next is to look at various examples of vector spaces, and we will immediately see that the examples that we consider, they satisfy all these axioms. Okay. So, now let us look at some common examples of vector spaces. So, the first examples of So, the first example is the usual 3D Cartesian space. Okay. It's actually a 3D space represented by Cartesian coordinates. Okay. So, any vector is so the vector has vector v has three components, vx, vy, and vz. Okay. So, it can be expressed as these three components, or alternatively it can be written as vxi plus vyj plus vzk. Okay. These are essentially the same vector, but you just write it in different symbols. Okay. And you show it as an arrow going from the origin to that point. So, we, as we had seen before, you have the x, you have the three axes which we call x, y, and z, and you have an arrow. This is vx, vy, vz. This is a vector v. Okay. And these are the components along each of the axes. Okay. So, this is an example of a three-dimensional vector space. Okay. And it is very easy to see that if you take two vectors and you add them, you will get another vector. Similarly, if you multiply a vector by a scalar, you will get another vector. So, for example, if you had two vectors v1 and v2, then clearly v1 plus v2 is also a vector. Similarly, the 0 vector is nothing but 0 0 0. Okay, it is a vector of length 0, okay, and that is a member of this space. And similarly, for any vector you can define the negative of that vector. Okay. So, clearly this satisfies all the axioms of a vector space. So, the set of all possible vectors forms a vector space. Second example is that we said it is 3D Cartesian space. So, there is nothing special about 3. So, you can have 2D. So, 2D, or you can have 4D, 6D, etc. You can have any dimension, 7D, 8D. So, for example, in 2D space your vector v would have only two components, vx, vy, okay, whereas in a vector in 4-dimensional space, in 4D this vector would have 4 components, and let me just for convenience I will call it V1, V2, V3, V4, okay, and so on, and so you can write vector space in any number of dimensions. Remember, all these components are scalars, okay, and this is just a way of writing the vector, okay. So vector is an object in this 4-dimensional space, and it is typically written in this form, okay, and you can easily show that these also satisfy the axioms of a vector space. The third example that we are going to talk about is set of all let us say real functions, set of all real functions of a single variable. X, okay, set of all possible real functions of a single variable x. So suppose you have a variable x, okay, then a function of x is denoted by f of x, and f of x, and if you take the set of all possible functions, any possible function of a single variable, okay, then that will form a vector space. So you can easily show that by showing that clearly if f1 is a function of x and f2 is a function of x, then C1 f1 of x plus C2 f2 of x is another function of x, okay. So f1 and f2, if these are functions of x, then clearly C1 f1 plus C2 f2 is another function of x, and you can take any two functions, you can construct such combinations of them and you will get another function, okay. Similarly 0 is also a function of x, okay, and what this function does is you can have a function f of x equal to 0 for all x, okay. So this is the 0 function, okay. Just to remind you, function, you should think of functions as some sort of machine. You give a value of x and out you will get a number, okay, and the 0 function, basically you give any value of x, you will return 0, okay. So this is also a function, and then similarly you can define the inverse and you can show that it satisfies all the additivity, associativity and distributive properties. And now so here is an example of a very different set of objects that also forms a vector space. See, you are used to, and this sort of explains why we have to have a general definition of a vector space, okay. If we had just thought of arrows and pointing in some direction, a magnitude in a direction, then we would not be able to identify the set of all functions as a vector space, but the axioms of vector space allow us to treat this set of all functions also as a vector space, okay. Now you can extend this, you can say set of real functions of two variables, 2, 3, 4, etc. variables, okay. So for example f of x y, okay, the set of all possible functions of two variables, that also forms a vector space, and so on, okay. So again this is another example of a vector space which is more general than the conventional idea of vectors as objects having magnitude and a direction, okay. So we can immediately see the connection between vectors and you know how to think of functions as vectors in some sense. Okay. So let us look at one more example. Okay. This is set of all, just for a start I will start with 2 by 2 matrices C's with real numbers as component. Okay. So, set of all 2 by 2 matrices with real numbers as their components or elements. So, for example, you can have a matrix A, B, C, D. Okay. Now, if you consider the set of all possible matrices, okay, all possible 2 by 2 matrices, that will also form a vector space, because you add any 2 matrices you will get another matrix. Okay. You can always define a 0 matrix and so on. Okay. And again, there is nothing special about 2 by 2. You can consider 3 by 3, 4 by 4, okay, but you take the same, you keep the same dimension, then the set of all matrices of particular dimensions will form a vector space. The last, I will give you one more example, and then we will stop for today. This is the set of all polynomials of degree n, okay, where n can be 0, n can be 2, 3, 4, 5, anything. Okay. So, a polynomial of degree n is typically written as a0 plus a1x plus a2x square plus an x raised to n. Okay. So, a polynomial of degree n means you can go only up to a n, you do not have any terms that are greater than n. Okay. Now, if you take the set of all possible such polynomials, they will also form a vector space. So, if you take any 2 polynomials and you add them, you will get another polynomial and so on. Okay. And n can be any number. Okay. You can start at 1, 2, 3, anywhere. Okay. Polynomial of degree 0 is a scalar. Okay. So, that is typically not called a vector, but from degree 1 onwards you can take any number and you will get a vector space. Okay. So these are some examples of vector spaces, and what I hope I have convinced you is that generalizing the definition of vectors and using a rather abstract definition, we are able to bring a lot more objects that we do not usually think of as vectors into this same description. Okay. Now, notice that the axioms of a vector space do not say anything about multiplication of vectors. Okay. So, indeed, in order to define something as a vector space, you do not need to define multiplication. You do not need to say what happens when you multiply 2 vectors. Okay. And what you know from your vector analysis is that there are many ways to take products of vectors. There is a dot product or the cross product or triple products and so on. Okay. So, there is no unique definition of the product of vectors, and so this actually is what we will start discussing in the next class. We will look at different ways to look at products of vectors.